Welcome back, everyone. So in this lesson, we're going to talk about an average rate of change again. So we're going to continue on from the previous lesson, and then we're going to add in what we call regressions, but we'll get to that in a bit. So we're going to start off with just kind of recapping and talking more about average rates of change. So this first page is really just kind of a warm-up just to kind of give you a deeper dive into average rates of change with nonlinear functions. So for this first one, we give you the function on the graph, and you are going to find the average rate of change between each of these points that are specified in this table. So I already have it filled out for you guys right here. That way you guys can kind of take a look. So the average rate of change from, say, A to B, which is going to give you that -5 halves. The average rate of change from B to C, which gives you -3 halves. Average rate of change from C to D, which gives you -1 half, and then so on and so forth. So when we find that average rate of change, what we're really looking for you to notice is what's happening to the values as we move further along in our function. So these are each going to be equal width intervals, and we're looking, well, actually, we're just going to look at just these. And then if we look at a non-equal length interval, then that's what that one is. But notice how the values in purple, the numbers are getting bigger and bigger as we go along, which that's what is showing for the slope. So if I were to find the slope at these specific points, what's going to happen is the slope is getting bigger and bigger as we move along. So when the slope is getting bigger and bigger, what that tells you is the average rate of change is going to be increasing. So because the average rate of change is increasing, that's what tells us that your graph is going to be concave up. And then same idea down here below is we're looking at the average rate of change if our graph is facing down. So as we know, this would be concave down. But when I look at the average rate of change over these intervals, then notice how we're going from, say, 5 to 3 to 1, -1, -3, -5, -7. The average rate of change is getting smaller and smaller, meaning it's getting closer and closer to negative infinity. So it's getting more and more negative per se. So because the average rate of change, or the slope rather, is getting further and further negative, it's decreasing. And because the average rate of change is decreasing, that tells us that your graph is going to be concave down. So really we're looking at the connection between the average rate of change and how that relates to the concavity. So if the average rate of change is increasing, concave up. If the average rate of change is decreasing, we're concave down. So using that knowledge, we're going to kind of expand on that. So moving on. So for any linear function, the average rate of change over any length input, the value interval is constant. We often think of this as the slope of the line. So it's still what you guys have been doing since y'all could practically walk. So the table gives selected values of the function f of x, and you want to explain why f of x is not a linear function. So just kind of a recap. If I were to do a linear function, and I'm going to take, say, let's just do these 3 points. So I can find the average rate of change from A to B, and that would be the slope here. And then I can find the average rate of change from, say, B to C, and this could be the slope here. These slopes, in order for it to be linear, must be equal. If they're not equal, that tells you it's nonlinear. So that's what we're going to do essentially with this drawing, or rather this table. Move over there. So starting off, I know there's an easier and probably quicker way to do this, but once again, I'm going to use average rate of change. So starting off, I'm going to do from 1 to 2. So my average rate of change so I'm doing from f of 2 minus f of 1 over 2 minus 1. So the output of 2 is going to give you 7 minus the output of 1, which is 4, over 2 minus 1, which is 1, which is going to give you an average rate of change of 3. So now we're going to move on and do the next set. So I'm going to do the average rate of change from the values 2 to 4. So when I look here, so we're going to do f of 4 minus f of 2 over 4 minus 2. So the output at 4 is going to give you 10 minus the output at 2, which gives you 7, over 4 minus 2, which is 2, which this is going to give you 3 over 2. So what you're looking at here is notice how the average rates of change are not the same. So we're going from 3 to 3/2. So automatically, I know this function is going to be nonlinear. So the reason you're going to, or the explanation that you're going to provide, so f of x is nonlinear because the AROC is not the same or not equal over all intervals. Or at least something along those lines. All right, moving on. So now number 4, so you're going to consider the quadratic function f of x equals x squared. And we're going to complete the table of values for g of x over the consecutive equal length input values below, or intervals below. I can't read, it's fine. Then we're going to find or complete the table for the average rates of change of g of x for each consecutive interval of equal length input values. So g of x over here, this is just doing the x value squared. So if I square -3, that's going to give us 9. If you square -1, that gives you 1. Square 1, you get 1. Square 3, you get 9. Square 5, you get 25. So with that, now we're going to find the average rate of change of this function over these specific intervals. So first off, I want to find the average rate of change from -3 to -1. So the average rate of change so I'm going to do g of -1 minus g of -3 over -1 minus -3. So the output at -1 is going to be just +1. And then minus the output at -3, which is 9, over -1 plus 3, which this is going to give you -8 over 2, which is going to give you an average rate of change of -4. So now we're going to do the same idea for the next 3. So I would say pause here and try the next 3 on your own. That's an R. So now we're going to do from -1 to +1. Whoops, I got that backwards. So the output at 1, which is just going to be 1, minus the output at -1, which is also 1, over 1 minus -1, which is going to be 2, which means we have 0 over 2, which this is 0. So be careful not to get that mixed up with 2 over 0. 2 over 0 is undefined. Remember, the one number you cannot divide by is 0. So this is undefined. 0 over a number, that is 0. So be careful with that. Moving on to the next interval. Oh, probably should actually put my numbers here. So now we're going to go from 1 to 3. So the average rate of change from 1 to 3. So g of 3 minus g of 1 over 3 minus 1. So the output at 3, which would be 9, minus the output at 1, which would be 1, over 3 minus 1, that's a 3. So 9 minus 1, which is going to give you 8, over 3 minus 1, which is 2, which simplifies to 4. And last but not least, now we want to do the interval from 3 to 5. So g of 5 minus g of 3 over 5 minus 3. So your output at 5, which is going to be 25, minus your output at 3, which is going to be 9, over 5 minus 3, which is just 2. So 25 minus 9, which is going to give you 16 over 2, which simplifies and gives you 8. So notice how, we're going to touch on this in the next part, but notice how your average rates of change, how they are increasing as we go along. So we're going from -4 to 0 to 4 to 8. Now notice how they're increasing at a pattern of +4. So because the average rate of change is constant at +4, not only is it going to be concave up, but because the average rate of change is the same, that also tells you it's going to be quadratic. So we're going to be even using average rates of change to prove whether a function is linear or quadratic, which that's what the next section is going to be. Well, let's actually touch on this. So this part right here. So there's a couple things that you need to know. So first off, so the AROC whoops, hold on. I'm losing my train of thought. There was a specific way I wanted to word this, and I have it written. There we go. All right, here we go. So first off, the average rate of change is not constant. Now, when I say that, that means if it was constant, that means it would be the same number at all of these, which it's not, so it's not constant. So what this tells you, because the average rate of change is not the same at all those points, that means it's nonlinear. And then the next thing that you also need to pay attention to is that your AROC is increasing. And then if your AROC is increasing, what that tells you is that it's going to be concave up. And then kind of a addendum to this, increasing at equal rate, then more specifically, that would mean it's quadratic. So that's what you want to notice about this previous problem. All right, moving on. So at this next set, now you want to look at the selected values in various functions that are given. For each table, determine if the function could be linear, quadratic, or neither. So we're going to be doing the average rate of change like we did up here, and we're going to look at the average rate of change to determine what type of function it could be. So over here, so I'm going to find the average rate of change from 1 to 2. So I know this is annoying, but I'm going to kind of shorthand it a little bit. So f of 2 minus f of 1 over 2 minus 1. So that's going to be 1 minus 0, which is 1, over 2 minus 1, which is just 1, which is just 1. So looking at the next one, then I'm going to do f of 3 minus f of 2, and that's over 3 minus 2. So the output at 3, which is 4, minus the output at 2, which is 1, over 3 minus 2, which is 1, well, that gives you 3. Okay, so looking at this so far, I have 1 and I have 3 for my average rates of change. So what this tells me is because they're not the same, it can't be linear, but I do see that it's increasing. So that tells me it's nonlinear. Now we want to see if it's going to increase at the same rate, which would make it quadratic. So now when I do the next one, so I'm going to do f of 4 minus f of 3 over 4 minus 3. So my output value here would be 9 minus 4 over 1, which would be 5. So when I look at my average rate of change here, notice how the average rates of change are changing at the same rate. So because they're changing at the same rate, that tells me that this function is quadratic. So now let's look at the next one. So same idea. I'm going to try to go through these kind of quick. So, whoops. Let's see if you can actually figure out kind of a very small but fatal error that I just made in this. What letter should I have used? I should have been using H. Whoopsies. So let me go back and fix these, which I know it seems silly to go back, but with AP Pre-Cal, the notation and how you write it is just as important as the actual answer itself. So bad notation will actually get you points off. So you got to double check, make sure you're using the correct notation, which I didn't, so that's my fault. So for this one, I'm doing g of 2 minus g of 1, and that's going to be over 2 minus 1. And then the output at 2, which is 1, minus the output at 1, which is 0, over 2 minus 1, which is 1. So that's going to give you an AROC of 1 for this interval. Now, same idea. I'm going to do g of 5 minus g of 2 over 5 minus 2. So the output at 5, which is 4, minus the output at 2, which is 1, over 5 minus 2, which is 3. So 4 minus 1 is going to be 3 over 3, which is going to be 1. So far we have the exact same AROC. So what this tells me is that it could be linear, but we still need to check the last interval and check and see. So I'm going to do g of 10 minus g of 5, and that's going to be over 10 minus 5. So 9 minus 4 over 5, which is 5 over 5, which is 1. So because all of the average rates of change are the same, so 1, 1, 1, it's 1 throughout, that tells me it's going to be linear. Alrighty, and last but not least, so now I'm using f in this one, so make sure I use the correct letter. So f of 2 minus f of 1 over 2 minus 1. So we're going to have 1 minus 0 over 1, which is 1. Next, we're going to have f of 4 minus f of 2 over 4 minus 2. So this is going to translate into 4 minus 1 over 2, which is 3 halves. So far we have 1 and 3 halves, so it's not linear. And then if we increase by 0.5, so if we go to 2, then it would be quadratic, but we want to see if the average rate of change is going to change at an equal rate. So now, let's do f of 7 minus f of 4 over 7 minus 4. So my outputs, we're going to have 9 minus 4 over 7 minus 4. So that's going to be 5 over 3. So it's not increasing or changing at the same rate, so all we can say about this is that it is nonlinear. But really, it's just neither. It's neither linear. It's neither linear nor quadratic, so really the answer would be neither. All right, moving on to the next part. So now we're going to look at the average rate of change and see how that relates to the concavity. So just like you did on the warm-up. So now we're going to take a look at this. Looking for my page. Okay, so the average rate of change over equal length input intervals is increasing for these functions. And then if it's concave down, it's going to be decreasing. I know I have such beautiful handwriting. All right, so we're still going to be looking at the average rate of change. So we're still going to be doing the same process that we did up here. Now, if you look at your values, notice how you're going to be throwing in some decimals. So I'm going to have my calculator over here with me to the side. You're more than welcome to use a calculator for these. Just know that if we give you pretty values like these, then you could expect that these questions would be a non-calc question. But if we give you some kind of gnarly decimals, just know that those most likely will be calculator questions. So starting off, so we are using k of x. So we're going to do k of 1.1 minus k of 1. And that's going to be over 1.1 minus 1. So that's going to be 1 minus 4 over 1.1 minus 1. So that's going to be 1 minus 4 over 1.1 minus 1. which that's going to give you negative 30. So for the next one, so now we're going to do k of 1.2 minus k of 1.1, and that's going to be over 1.2 minus 1.1. So that is going to translate to negative 1 minus 1 over 1.2 minus 1.1. So negative 1 minus 1, 1.2 minus 1.1. So that's going to give you negative 20. And then for the last one, so k of 1.3 minus k of 1.2 over 1.3 minus 1.2. So the output would be negative 2 minus negative 1 over 1.3 minus 1.2. Which is going to give you negative 10. So notice how your AROCs were getting closer and closer. So think of the number line. So I have negative 30, negative 20, negative 10. So we're moving further and further to positive infinity. So that means your AROC is getting bigger. So your AROC is increasing. Which, from that information, what that tells you, I can't spell, is that your function here is going to be concave up. So that's what we're looking at. So same idea for B and C. I would highly recommend pausing here, trying B and C on your own, and seeing if you get the same thing that I do. All right. So I'm going to jump over to part C, and then I'll come back and do part B. Okay, so now we're working with P of X. Okay, so with P of X, we're going to do P of 1.1 minus P of 1, and that's going to be over 1.1 minus 1. So we are working with 7 minus 1 over 1.1 minus 1. Which, in that case, I believe that's going to be 60 if I'm doing my mental math correct. But of course, I'm always going to double check myself. And it is. Yay. All right, next. So now we're going to do P of 1.2 minus P of 1.1 over 1.2 minus 1.1. So we're going to have 11 over 7. Over just 0.1. So that, if I'm doing my mental math correct, that should also be 60. Ooh, nope, it is 40. Math is hard, y'all. That's, yeah, it's 4 over 0.1, so it's 40. All right, and then next we're going to do P of 1.3 minus P of 1.2. That's going to be over 1.3 minus 1.2. So for this one, we're going to have 13 minus 11 over 0.1, and that should be 20. So in this case, yes. Now, if you look at your average rate of change, we're going from 60 to 40 to 20. So my slope starts off 60 over 1, which is going to be very steep. And then we're going to go to 40 over 1, which is less steep. And then we're going to 20, which is going to be still increasing, but less steep. So it's going to follow a concave down pattern. Let's see if I can erase this without erasing everything. So in this case, AROC is decreasing. Which means concave down. All right, now I'm going to go back to part B and see what happens here. So when I do my average rate of change, now we're working with the letter M. So I'm going to do M of 1.1 minus M of 1 over 1.1 minus 1. So that's going to be 4 minus 1 over 0.1, which is going to be 30. Yep, I'm always going to double check myself. Mental math is hard, y'all. Okay, so now looking at the next one. So M of 1.2 minus, M of 1.1 over 1.2 minus 1.1. So that's going to be 7 minus 4 over 0.1, which is still going to be 30. So we have the same average rate of change so far. So now I'm going to do M of 1.3 minus M of 1.1 over 1.3 minus 1.1. So 10 minus 7 over 0.1, which is also 30. So because we have the exact same average rate of change, so that tells you, I cannot draw a capital R. The average rate of change is constant, which means your graph is going to be linear. But we're asking for concavity, and because it's linear, there is no concavity. So that's how you would answer this one, when there is no concavity. All right, so for the regressions, that's very calculator heavy, so I'm actually going to do a separate video for that one. So hopefully you're good with average rates of change. See you in a bit.